Get ready, quantum enthusiasts. We're diving into mind-blowing breakthroughs in quantum computing that could change everything. First up, scientists have achieved over 99% fidelity with scalable, hardware-efficient multi-qubit CCZ gates. Next, we're exploring how genetic algorithms are designing variational ansatze for high expressibility and shallow depth, a game-changer for quantum algorithms. Then, get ready for quantum error correction, achieving low-crosstalk readout with drag-inspired pulse shaping, a crucial step for building fault-tolerant quantum computers. And finally, RIBER is securing major ROSIE orders from U.S. quantum computing firms, pushing the boundaries of silicon photonics. Stick around, you won't want to miss this. Hit that subscribe button and ring the notification bell so you never miss an update. Quantum gate fidelity skyrockets. Scientists have achieved a significant breakthrough in quantum computing by demonstrating a new method for implementing a high-fidelity controlled Z (CCZ) gate, a crucial operation for complex quantum circuits. This innovative approach utilizes two-photon absorption in superconducting qubits, offering a pathway to substantially reduce circuit complexity and improve performance. The team successfully designed a scheme that achieves a simulated fidelity exceeding 99% within a remarkably short timeframe of 194 nanoseconds, representing a substantial improvement over existing methods. This new CCZ gate surpasses previous implementations that rely on breaking down the operation into sequences of single-qubit and two-qubit gates, which introduce both delays and inaccuracies. Detailed simulations confirmed the scheme's resilience to variations in system parameters, validating its practicality for real-world applications. Furthermore, the team extended the functionality of this approach to create CC phase gates with arbitrary angles and scalable multi-qubit operations, including the realization of CCCCZ and CNZ gates. This scalability is critical for building more powerful and versatile quantum computers, capable of tackling increasingly complex problems. The breakthrough delivers a pathway towards substantial depth compression in quantum circuits, paving the way for transformative quantum algorithms and simulations in fields like materials science, drug discovery, and financial modeling. This research demonstrates a hardware-efficient method for directly implementing a CCZ gate on a superconducting circuit, achieving a simulated fidelity exceeding 99% within 194 nanoseconds. The approach utilizes two-photon absorption and offers advantages over existing methods that rely on breaking down the gate into sequences of single- and two-qubit operations, resulting in both lower latency and improved overall fidelity. Importantly, the scheme exhibits robustness against variations in experimental parameters and can be extended to create continuous parametric families of three-qubit phase gates, offering versatility for complex circuit compilation. The findings establish a practical pathway towards realizing near-term quantum applications by significantly reducing circuit depth through native multi-qubit interactions and enhancing operational fidelity. This incredible leap in quantum gate fidelity is just the beginning. Next, we'll see how genetic algorithms are revolutionizing circuit design. AI designs smarter quantum circuits. Scientists have developed a novel genetic algorithm-inspired framework for designing variational quantum circuits, achieving high expressibility while maintaining shallow depth and a low parameter count. This breakthrough addresses a critical challenge in quantum computing, where circuits must be both powerful enough to represent complex quantum states and trainable on near-term quantum devices. The team's approach evolves circuit designs through mutation and selection, guided by an expressibility metric, consistently generating circuits that perform comparably to traditional designs but avoid the limitations of barren plateaus, a phenomenon that hinders optimization. Experiments demonstrate the effectiveness of this new framework across a range of molecular systems, including H2, LiH, BH2, and H2O, and a non-molecular transverse field Ising model. The circuits were benchmarked against established ansatze designs like unitary coupled cluster with singles and doubles, UCCSD, and ADAPT-VQE, demonstrating competitive performance. Researchers assessed expressibility using a fidelity-based method, quantifying how well the generated circuits explore the Hilbert space and approximate the uniform Haar distribution. Results show that the newly designed circuits consistently achieve high expressibility at any target depth, offering a scalable solution for a wide range of applications. While UCCSD and ADAPT-VQE are established methods, their computational cost scales rapidly with system size, limiting their applicability to larger molecules. The new framework overcomes this limitation, offering a pathway to designing expressive, low-depth circuits that require design only once and can be applied to diverse quantum computing tasks. This advancement promises to accelerate progress in areas like materials science, drug discovery, and fundamental quantum simulations. This research introduces a new method for designing variational quantum circuits, known as ansatze, which are essential components of many quantum algorithms. The team developed a genetic algorithm-inspired framework that automatically evolves circuits to achieve both high expressibility, the ability to represent a wide range of quantum states, and shallow depth, meaning they require fewer quantum operations. This approach addresses a key challenge in the field, as traditionally, increasing expressibility often comes at the cost of making circuits more difficult to train and susceptible to errors. The resulting ansatze consistently demonstrates strong performance across various molecular and non-molecular systems, matching the capabilities of established designs while avoiding the issues associated with barren plateaus, a phenomenon that hinders optimization. This work provides a general and scalable solution for ansatze design, offering circuits that can be created once and applied to a broad range of quantum computing applications. The authors acknowledge that the performance of these circuits, like all variational algorithms, still depends on the effectiveness of the classical optimization process used to train them. With smarter circuits being designed, the next challenge is making sure our quantum computers can accurately read their states. We're talking about error correction with pulse shaping. Quantum error correction gets a clarity boost. Scientists have developed a novel pulse shaping technique to dramatically suppress measurement crosstalk in quantum systems, a critical step towards building scalable quantum computers. This breakthrough addresses a fundamental challenge: fast, multiplexed readout, essential for efficient quantum processing, introduces unwanted signal interference that degrades qubit performance. The team's method, inspired by the derivative removal by adiabatic gate, drag, protocol, effectively mitigates this crosstalk by carefully engineering the spectral content of readout pulses. Experiments demonstrate that applying drag introduces no measurable degradation in qubit readout fidelity across a broad range of notch frequencies, spanning from 13 to 201 MHz. By creating a spectral notch at frequencies neighboring the target resonator, the technique minimizes spurious signal interference, preserving qubit coherence. Ramsey experiments revealed that implementing drag extends qubit coherence times to 1.41 μs, a substantial improvement over systems without this spectral shaping. This enhancement is achieved by suppressing a pronounced beating pattern observed in standard Ramsey oscillations, indicating a significant reduction in qubit dephasing. Further measurements of readout-induced qubit dephasing confirm the effectiveness of the drag technique. The team observed a substantial suppression of additional errors induced by stray readout pulses, with theoretical calculations exhibiting excellent agreement with experimental data. Specifically, the technique minimizes the impact of the pseudo-readout pulse on qubit coherence, allowing for more accurate and reliable quantum measurements. This advancement paves the way for denser and more complex quantum circuits, bringing scalable quantum computing closer to reality. The method seamlessly integrates with existing readout architectures without requiring additional hardware, making it a practical and readily implementable solution for improving quantum system performance. This research addresses a key challenge in scaling up quantum computers, efficiently reading out the state of multiple qubits. The team demonstrates that fast measurement pulses, while improving readout speed, introduce unwanted interference, crosstalk, between qubits due to spectral broadening. This crosstalk degrades the accuracy of the measurements. To overcome this, They developed a pulse-shaping technique, inspired by established methods in quantum control, that suppresses this interference by carefully engineering the frequency spectrum of the measurement pulses. The method effectively creates a notch in the pulse spectrum, minimizing signal leakage into neighboring qubits resonators. Importantly, this technique integrates seamlessly with existing quantum computing hardware, requiring no additional components. The results show a significant reduction in crosstalk, paving the way for faster and more reliable multiplexed qubit readout. While acknowledging that the technique is most effective when qubits are not identically spaced, the authors suggest potential extensions, including combining it with existing filtering architectures and exploring balanced pulse shaping for systems with both positively and negatively detuned neighbors. Future work could also integrate this pulse shaping with other techniques designed to further enhance readout fidelity and speed. So, we've seen incredible progress in quantum gates, circuit design, and error correction. But how is this all translating into real-world hardware? We've got an exciting order from a US quantum computing firm that could be a game changer. Quantum hardware milestone achieved. RIBER announced on 8 September 2025 that it has secured its first United States order for a ROSIE system from a leading quantum computing company. The order marks a pivotal moment for the company, signaling that the fully automated ROSIE platform, designed for the precise growth of thin oxide layers on 300 silicon wafers, has earned the confidence of a high-profile US customer in the quantum technology sector. The deal follows RIBER's earlier collaboration with the Novo Nordisk Foundation Quantum Computing Program, NQCP, in Denmark, underscoring the platform's growing credibility across the global quantum computing ecosystem. The ROSIE system is engineered to deposit barium titanate thin films with exceptional uniformity and defect control, a material that is increasingly recognized as a cornerstone for integrated electro-optic modulators. By automating the deposition process, ROSIE eliminates many of the manual steps that traditionally limit throughput and reproducibility in molecular beam epitaxy. Its compatibility with 300 wafers aligns it with the industry's move toward larger substrates, enabling scalable production of photonic devices that can be seamlessly integrated into silicon-based quantum processors. The new US order is slated for delivery in 2026, with ROSIE's commercial industrialization scheduled for 2027. This timeline reflects RIBER's strategic roadmap to bring the platform from laboratory validation to mass production, thereby accelerating the deployment of silicon photonics solutions that underpin next-generation quantum technologies. The partnership with the US quantum computing leader not only validates ROSIE's technical capabilities, but also positions RIBER at the forefront of the semiconductor industry's shift toward integrated, high-performance photonic components. Founded in 1964 and headquartered in Bezons, France, RIBER has long been a pioneer in molecular beam epitaxy, MBE technology. The company announced on 8 September 2025 that a new US quantum computing enterprise has placed an order for its ROSIE platform, a fully automated MBE system engineered to deposit barium titanate thin films onto 300 silicon substrates. The order marks the first commercial transaction of ROSIE in the United States and underscores the platform's readiness for large-scale silicon photonics production. The ROSIE system streamlines the growth of the material by automating the deposition sequence, thereby reducing manual intervention and enhancing repeatability. Its design incorporates advanced flux control and real-time monitoring, which together maintain film uniformity and minimize defect density across the wafer surface. These attributes are essential for the fabrication of electro-optic modulators that must operate with high fidelity in integrated quantum photonic circuits. The collaboration with the Novo Nordisk Foundation Quantum Computing Program in Denmark, announced last June, provided a critical validation of ROSIE's capabilities in a research setting. Building on that partnership, the US order is scheduled for installation in 2026, with a full commercial rollout slated for 2027. This timeline reflects RIBER's commitment to transitioning the platform from laboratory demonstration to mass production within the next few years. By securing this order, RIBER is reinforcing its leadership in the evolving silicon-based photonics arena, positioning its MBE solutions at the heart of next-generation quantum technologies. The ability to reliably grow barium, titanate thin films on 300 wafers will accelerate the deployment of high-performance electro-optic devices, thereby supporting the broader semiconductor ecosystem's shift toward integrated, scalable quantum processors. The collaboration announced in June 2025 between RIBER and the Novo Nordisk Foundation Quantum Computing Program, NQCP, in Denmark, marks a pivotal endorsement of the ROSIE platform beyond the United States. NQCP, a research arm of the Novo Nordisk Foundation, is a prominent Danish initiative that funds cutting-edge quantum computing projects. By partnering with NQCP, RIBER secured a research-grade validation of ROSIE's ability to grow barium, titanate thin films on 300 silicon wafers, a critical material for electro-optic modulators in integrated photonic circuits. This partnership demonstrates that ROSIE's fully automated molecular beam epitaxy system can meet the stringent demands of European quantum computing research. The collaboration, formally announced last June, provided a testbed for the platform's flux control, real-time monitoring, and wafer-scale uniformity, features that are essential for producing high-performance electro-optic devices. The fact that a leading Danish program has adopted ROSIE for its experimental programs signals a strong international confidence in the technology, complementing the recent U.S. order and reinforcing RIBER's position as a supplier of next-generation photonic components. And that wraps up another incredible episode of Metaverse Update. We saw scientists achieve over 99% fidelity with scalable, hardware-efficient multi-qubit CCZ gates, genetic algorithms designing variational ansatze for high expressibility and shallow depth, quantum error correction achieving low-crosstalk readout with drag-inspired pulse shaping, and RIBER securing a major ROSIE order from a U.S. quantum computing firm. Don't forget to like this video, subscribe to the channel, hit that notification bell, leave a comment with your thoughts, and follow us on all our social media channels for more quantum insights. See you next time.